When you go to do a chi-square test in Excel, if you look at the original format of the data where we have one person on each row, we ultimately are going to need to kind of tabulate that, shift that into a frequency table. And you have some experience with frequency tables, but it's been a while since we used them, so I'm going to kind of walk you through creating those frequency tables. So here we have a more traditional layout for the data where the first individual, their ethnicity is 1, their poverty level is also 1, and we can then do tabulations. And so here I already have it worked out so I can focus on talking you through this. But when we look at this, if we tabulate, and you can see that what I'm doing is saying I'm count if, and there's an S, so I'm going to have multiple criteria. Count if A2 through A101, because there was 100 individuals in our sample, is a 1, and those are the individuals that their ethnicity is white. Count those individuals if they also are above the poverty threshold. So 1 means they're above the poverty threshold, 2 means that they are, or 0 means that they're below the poverty threshold. So what we're going to do is then count those individuals, and we find that there are 60 individuals that are both white and above the poverty threshold. The next line, most of it's the same, so we're still looking at A2 to A101. We're still looking at if those individuals from A2 to A101 are white. On B2 to B101 though, that's where we're saying, okay, now I'm interested in the white individuals that are below the poverty threshold with 0 representing that they are below it. If the numbers throw you off, you could always change this. And in fact, if this said white over here, you could then use that as your criteria. You would just need to put it in quotes. So you would be in here, and if we, instead of using 1, used white, you would then just need to write that out. And then it would look for how many times does that occur. Of course, that occurs 0 time in the way that I have the data set up, but you can use that. SPSS doesn't like it as much, but given that we're not using SPSS for the remainder of the semester, that wouldn't be a problem if you wanted to convert the ethnicities to 1 is white, 2 is black, and 3 is Hispanic or Chicana. When you get to the next one, same basic code. We still want to know if they are above the poverty threshold, so that's going to be similar to the row that's next to it. What changes is now the ethnicity is 2. 2 are individuals who are black. So we go through, we do each of these cells. Over here you see the basics of the code. And so each case we're going to be looking at A2 to A101 and B2 to B101. And then the only part that's changing is this part, and I'll highlight the part that's going to change in each case. Or we'll bold it. Is this part of the code where we indicate the ethnicity that we're interested in or whether they are above the poverty threshold. Now, the 1 and 0 are actually going to stay the same in respect to the rows. So the top row will always have a 1 for B2 to B101 because those are the individuals above the poverty threshold. The bottom row in here, right, will always have a 0 in relation to B2, B101 because we're interested in are they below the poverty threshold, which is represented by 0. And then as we move from E to F to G, this bolded section here changes from 1 to 2 to 3, and we can see that in our code here, where the next one is 2, and the one after that is 3, but otherwise the code is identical to what we saw before. And of course, these answers are available to you, so if I'm walking through it a little bit too fast, you can always look at the code. You should try to still walk through it on your own though, and by now I anticipate that you've had enough experience that you know that it really is important to practice this, to walk through it, and then to double check your answer. For this total, so this is the total column, we can just use sum. So we can sum the first row, sum the second row, Same thing for the column totals. We just sum the column. So we find out that there are 67 total white people, 19 total black people, 14 total Chicano. And in fact, those, again, ignoring other groups, Asian, Native American, Native Hawaiian, are pretty much the distributions. Most of the country is still predominantly white. There's 67%, give or take. About 19-20% of individuals are black. And nationwide, it is true that about 14% of individuals are Hispanic, Chicana, Latino, Tejano. Unfortunately, they get combined together when we're looking at census data a lot of the time. Of course, that is not true for every state, and in Texas, that definitely wouldn't fit. But nationwide, this is still pretty accurate with what we would expect. And that also would be a total row. And then the total of all people in our sample is 100. And we have that here. So 85 plus 15 equals 100. Also, 67 plus 19 plus 14 would give us 100. For the expected values, we talked about this in the other. That is going to be the row total times the column total, and then we're going to divide by the expected value. Now what I've done is I've made this code so that I can kind of copy it a little bit. So I've told it to hold steady on H2, H being my row total. So I can use that across each of these. And in fact, we find that we still are going to use H2 for the next one. And then, of course, we have the same number of individuals in all cases. So I've told it to stay static on H4 as the denominator in each of these. We do want to look at the different column, right? So as we move across the columns, we should go from E4 to F4, and then the last one we should see that as G4. But in each case, we stay on H2, and our denominator is always going to be H4. So again, the dollar sign here is telling it stays stationary on H, and because we have a dollar sign in front of 4, always 4. Now that's useful because then I can take what I have in this first row and I can then just copy it down as we've done before into the next row, because there we want to have E4 times H3, so the row total moves down. The column stays the same, so E4 and then F4 times H3 and then G4 times H3. So this gives us our expected values. And then what we're really interested in is those, or are those deviations. The deviations between the observed value here and the expected value, which is here. So this first cell is going to say, what's E2 minus E6? We want to square it to deal with the fact that some are going to be positive, some are going to be negative. Divide that by the expected value. So if you look back at the other video, we introduced the FO, frequency observed, minus frequency expected, divided by frequency expected. And then for the next one, same basic idea, frequency observed for the black individuals above the poverty threshold, minus the frequency expected for black individuals above the poverty threshold. Square that difference, square that deviation, divide it by the frequency expected. And so once you write this first one, you actually can just copy and paste to this whole block of cells. And that'll give you the deviation for white above, and then below it will be the deviation for white below, black above, black below, and then finally Chicana above the poverty threshold and below the poverty threshold. And so as there are deviations, as the number of people in a cell or in a group, in a condition, are different from what we would expect if they were evenly distributed, if there were the same number, percentage, proportion of white people who were above and below, as black people who were above and below, as Hispanic who were above and below. So raw numbers, they might be different. We 67% of the population is white, so the numbers are going to be larger, but proportionally, if they were distributed evenly, or it's the same as the black individuals are distributed and the way the Chicano individuals are distributed, we would see that this would be close to zero. The deviations would be relatively small. Once we get each of these cell deviations, we then add them together. So we saw that it was capital sigma, right? Meaning sum together, add those up. So I find this to be the easiest way. I just sum E9, right, through G10. So those are these cells here. And I find that my chi-square obtained is 3.6573, which is consistent with the video I just showed you. Now you could, should you want to, I don't know why you would, you could do this all in one really big, long function, and I have that here. All I'm doing is basically taking what's done, right? So the first part of this function, let's see if I can do this. Let's scroll back, there we go. So the first part of this function is what you see in that first cell that's at E9. So E2 minus E6, square that, divide by E6. So you could do it all together. Again, I think you're more likely to make a mistake. I know I would be more likely to make a mistake. If I do it this way, I can easily see, okay, I've got that cell set, and then I can just copy and paste so it does each cell for me, and then I can sum those, which also kind of reminds me about the formula, where do this for each individual cell, sum them together, right? Which is what that sigma represents. Now I can do the same thing for the data set with 200 individuals. And what I basically find is the proportions are the same. It's still that 85% of individuals are above the poverty threshold, but now in the data with 200 people, this number will be double, right? So if I have 200 people, 85% of 200 is now going to be 170. So we're going to look at that real quick. And in this case, literally what I've done to make sure that everything's the same and I've just increased the sample size is I have taken the data, the 100 individuals, and I just copy and pasted them to make it 200 people. That way I know that the distributions are identical. The proportion of people that are white and above the poverty threshold is identical in each of these two cases. It's just the sample size has doubled. So I'm going to borrow some of my code, and I think I should be able to just take this and paste it into my new data. There we go. And then, of course, I need to extend. So now instead of A101, I'm interested in A201 and B201. Same thing here. And of course, you could, of course, you could do this faster by highlighting these cells and going into find select and saying that I want to replace every place I see A101, I want to replace it with A201, replace all. I should see 3 replacements because I've already changed most of them. Same thing for B. So I want B101 to be B201. Again, 3 replacements. And now I do see that I have my 200 people represented. As I mentioned, this is double, so 85 times 2 would be 170. If I flip back to the data, 15 times 2 should give me 30. So again, the distributions, the proportions of individuals above the poverty threshold is the same. This is still 85% of the people, it's just 85% of the 200 people. Same thing here, 134. If I look at this, 67 times 2 is 134. 19 times 2 should give me 38. So these are double what they were before. So otherwise, it stays the same. Now, the nice thing about copying my code is all of this stays the same. I'm still interested in the row total for above times white divided by the total number of people. All those are in the same place. I should, if I wanted to double check that, the total for this row should still be 170. They've just been distributed differently. So if the 170 people were distributed related to proportional to the total number of white, total number of black, total number of Chicano, right? This is how it would look. This is the values we would expect. And then the same thing for the one below it. Still have 30 people represented by these expected values. 30 people are still below the poverty threshold. It's just that that's been distributed so that if they were equally represented across these ethnicities, what would those 30 people, 15% of the people, look like? And it should be that 20.1% or 21.1 people are going to be white, 5.7 people are going to be black, and 4.2 of the people below the threshold are going to be Chicano or Chicano. Are deviations then still automatically calculated? I'm still interested in the deviations for white above from the expected value. For white above, square that deviation, divide by the expected value. So that all updates. And as I mentioned, when I sum that together, when I sum those squared deviations divided by the frequency expected, I find that this value is almost double our original value of 3.6573. Again, it's not going to be exactly double, but that sample size plays a big role in whether or not this is going to be significant. Our critical value is still 5.99 because I have 3 categories on ethnicity. I have 2 categories on above or below the poverty threshold on that variable. So my degrees of freedom is still 3 minus 1 times 2 minus 1. So it's still 2. Thus, my critical value is still 5.99. And suddenly now, just because my sample size is larger, I'm going to get significance. Now, that can be problematic because basically what is always going to happen is this value right here is never going to perfectly equal this. And so all those little deviations are going to add up. And if I just get a big enough sample size, then pretty much I can almost guarantee that I'm going to reject the null hypothesis because the null is that these two are equal to each other, that the frequency observed and frequency expected are equal. The alternative is that they are different, that they are not equal. Well, unless they are perfectly equal, as I increase my n, inevitably I'm going to make it so that chi-square is large enough and thus significant, which goes back to, well, what about Cramer's V? And so if we take this obtained chi-square, so Cramer's V, if we flip back over, and I think I still have the PowerPoint up, was the chi-square divided by n plus degrees of freedom and take the square root of that quotient. So we're going to say square root, and we have the chi-square. We're going to divide that by n, which in this case is 200, plus our degrees of freedom smaller, which is still 1. And so we find that chi-square is a little bit different than it was before. If you remember before, and in fact you could go back over here, and if I line this up, so if I'm on E14 and I put it on E14 over here, should work that all my referencing works. So it has changed a little bit. Again, that's partially because of the formula. We're using a simple formula. If you did this in SPSS, and the data for SPSS is available, so those .sav files, that's SPSS data, and basically it just has these two columns in it, and then you can run the chi-square in SPSS, and you should be able to find a video to show you how to do that in YouTube or something like that. So don't trust YouTube for actual stats, the conceptual stuff. Sometimes you can get wrong information that way. But if it's just walking you through how to do something in SPSS, YouTube's pretty useful for that. And so if you look at these two values, our way of calculating them using the easier formula, we do end up with 0.19029 here, and we end up with 0.1907608 here. If you did it in SPSS, I think the values are actually identical between these two things because it uses a more sophisticated formula that better approximates the actual obtained effect while accounting for sample size and everything. So because of that, our values are a little bit off, but ultimately our decision would be the same, right? Roughly, Cramer's V is 0.19 in both scenarios, but the chi-square itself is considerably larger, again, proportionally influenced by sample size, so we have to keep that in consideration.